지난 시간에 저희 안 했다, 여기부터 안 했다고 하니까 이거부터 하고 그 오늘 수업 내용으로 넘어갑시다. So during the last class, so we talked about why proteins fold, and so what is the protein folding problem, and why proteins fold to its specific native structure, and so the main driving force of protein folding is generally the hydrophobic effects. The hydrophobic effect means that the non-polar residues, hydrophobic residues want to be buried inside the protein. So that is one of the major driving forces of protein folding. But in addition to that, so there are other non-bonded interactions. So here, so the non-bonded interaction means that is the interaction between atoms which are not connected by covalent bonds. So if two atoms are connected by covalent bonds, so they are very strongly connected. But if two atoms are not covalently connected, then they interact with non-bonded interactions. So the example of non-bonded interactions are hydrogen bonds and salt bridges. So the salt bridge means that ionic interaction. So ionic interaction means that, so what are the ions? Ions are the particles with charges, right? So the ionic interaction means that the electrostatic interaction between charged particles. So for example, so here these red dotted lines means that hydrogen bonds, so the interaction between hydrogen and the strong electron withdrawers. So they are forming very strong hydrogen bonds. And salt bridges. Salt bridge means that the interaction between charged groups. So for example, here this group is positively charged, and this carboxyl group is negatively charged, and so they are attracting each other. They are attracting each other very strongly because of this Coulomb interaction, so the electrostatic interaction. And van der Waals interaction is, so we all learned that the van der Waals interaction exists between all atoms, right? So the van der Waals interaction exists between all atoms, and also we also learned that van der Waals interactions are stronger for larger groups. So if side chains are large, then van der Waals interactions are generally larger. So for example, so for these molecules, so here, they are all methyl groups. So the methyl groups, hardly don't have, as you all know, so they are mostly, non-polar, right? So they don't have much charges. So charges are almost, the partial charges are almost zero, but still, so they are interacting. So they are still, so if they are close enough, so they are, attracting each other. So what is the form of van der Waals? So the van der Waals interactions are generally written like this, right? And the functional form is written like this, and so R over 12 over A minus R to the 6 over B. B over R to the 6, right? And so generally, so this term corresponds to the repulsive interaction. Repulsion, right? So the repulsion is repulsion means that the repulsion mainly plays a role in this region. So if two atoms are too close and they repel each other. And this term is for the attractive term. So generally it works here, right? So if two atoms are somewhat close, then they attract to each other. And you may have already learned about the origin of van der Waals interaction, right? So the van der Waals interactions are mainly caused by the fluctuation of electron clouds, right? Electron density. So although so one molecule is non-polar, but still so it has electron density, and electron density is not actually static. So it is fluctuating. So it fluctuates. Right. So although the net charge is zero, the whole the total charge might be 0, but sometimes so it fluctuates, and sometimes it becomes slightly positive and slightly negative, and then this one induces, this one affects this molecule and induces negative charge here and induces positive charge here, and so that is the fluctuation, and by doing this, so they are interacting, they are actually attracting each other. So this is called, dispersion interaction. Dispersion, or sometimes it's called, London dispersion energy or interaction. So here the London is the name of the scientist who first discovered this interaction, and this interaction is called the dispersion energy. So in general, in many cases, so dispersion energy is almost identical with the van der Waals interaction. So they are very similar term, but more specifically, so this term only corresponds to dispersion interaction, and actually, this repulsion term is because of Pauli's, mainly because of Pauli's exclusion principle. Most of you have already learned in physical chemistry class, right? So exclusion is CL principle. So that is the van der Waals interaction, and so here mostly between bulky side chain. Bulky means, so what does bulk mean? Bulky means just a large chunk, so just a large one. So the bulk means, we use those terms in daily life, right? So the bulk means, they're just large side chains. So the large side chains generally means that pentyl group or large rings, or has many side chains, many aliphatic side chains, something like that. So they are called bulky side chains. And in addition to that, in addition to those, so in proteins, there is one more specific interaction called disulfide bonds. So among 20 amino acids, actually, cysteine has sulfur at its side chain. So the cysteine has, at the end of cysteine, so this one is forming, SH group. So this one becomes SH group. And when two SH groups come close, so they can, and if they go, so reduction, reaction, then so they two, is it reduction or oxidation? It's oxidation, right? So the removal of hydrogen. So they go through oxidation reaction. So they lose H, and this one lose H, but instead so these two sulfur atoms can form a covalent bond, right? And this is disulfide bond, and this kind of disulfide bond is very common in protein. And as you can see, so this one is forming a covalent bond. So this one is very strong. So this one, once this is formed, so this is very strong and very hard to break. So they are forming a very strong restraints of protein structure. So here these yellow lines are showing the disulfide bond in protein structure, and once they are formed, and they are highly stable and they are really hard to break. So the disulfide bonds are playing also an important role in protein structure. And all the proteins we have talked about is, so the Anfinsen's principle is generally right, but in biology, so nothing is 100% correct, and so there's always exceptions, and something don't follow the laws, and so we learned that the most of the proteins got folded to its native structure by self, so without any help. They fold to its native structure spontaneously, but some proteins are not folded by themselves. And if they don't fold to their native structure by themselves, and they need help, some proteins need help to be folded. In those cases, so they need something called chaperone protein. Do you know what is chaperoning? So the chaperoning means a medieval knight, so who protects who guards a princess or high, noble people. So when there's a princess, so there's always, guards, right? So knights who protect her. So the chaperoning means that it is a word from French, and the chaperoning it means guard or bodyguard or something like that. And so these proteins need help to be folded. So sometimes, so this is the structure of chaperoning protein, called Groeil structure. So this is a gigantic protein, and this is actually the lead. So this is the cover. And so once it is open, sometimes, so some proteins go inside this chamber, and it is folded to its native structure, and once folding is done, then it is open again and goes outside. So some proteins need help, and for those cases, so some proteins like this one is needed. And this kind of protein is also very common, and sometimes, so here it is showing that so unfolded protein goes into chaperoning protein, and it is folded inside the chaperoning, and after that, it is escaped from chaperoning, and it works. So that is the example of protein chaperoning, and this is also a very active area of research these days. So let's wrap up the protein structure, protein folding topic here, and let's switch to the basics of protein-ligand docking. So many of you have seen protein structures using Chimera during the practice session, right? So and during the next class, so we're gonna do protein-ligand docking. So the protein-ligand docking, and so. So today, so we're going to talk about the basics of protein-ligand docking. Oops. I made a mistake. So I should have downloaded PowerPoint. So this is the picture of spaceship, and this is. Let's forget about it. So what is docking? So the docking. You may have heard about docking station. So actually, so that was the picture of docking station of iPhone. Actually, those things, right? Dock your, cell phones, and you can play as a speaker, or you can charge your phone or something like that, right? And also, so docking. You already have heard about the word docking from when two space shuttles, combined together. So we call it docking, right? But the similar concept is used in protein science also. So in protein science, so we call docking as ligand is docked with protein. So the dock means so something is something is bound. Yeah. But in protein science, so docking means that so docking simulation attempts to find the best matching between two molecules. So let's go a little deeper. So the protein-ligand docking is a molecular modeling technique. And so the goal of protein-ligand docking is to predict the structure, predict the position of ligand, and also so which means that the orientation of, in other words, orientation of ligand, so when it is bound to a protein. So let's imagine that so you don't have this ligand. So we know that so this is the drug, and so we know that so this one will bind to here, but we don't know how it binds. So we don't know its pose. So then so the docking means that so we predict the bound pose of this complex. So the complex means that the protein and ligand together. So the structure of the complex using computer. Then why is protein-ligand docking important? Actually, so the many proteins, as we have talked before, so many proteins are regulated. So the regulated means, so in biology, so regulated, the word regulated is used quite frequently, but the regulated means control. So the many proteins are controlled by the binding and unbinding of ligand. So that is a signal. So it is like a switch. So the binding and unbinding of ligand means so it turns off or turns on a certain protein. So the one of the well-known example is something called hormone. So the hormone is a ligand produced in our body, and so the hormone goes to some specific position, then it gives a signal to some certain cells, and cells, based on hormone level, so cells sometimes work or sometimes stops working or something like that. And therefore, they play important roles in drug discovery. So the most of the drugs are actually ligands, and actually most of drugs actually bind to certain protein. So most of the drugs are actually considered as ligands. So by using protein-ligand docking, so we can find, so the drug candidates can be efficiently searched from chemical databases. So in chemical databases, there are thousands and thousands of, actually more than thousands, so how many? About billions of, chemical structures are known, but we don't know which one is drug or not, or which one can be drug or not. So in order to identify, in order to judge, so which one will be a drug candidate, so we need to predict so how they will bind to a protein. And also, based on the structure of protein-ligand complexes, so we can design new drugs. So if we know the structure of protein-ligand complex, if we know the structure, for example, if we know how they are interacting, then so we can think that, so if I mutate this residue into something else, then they will bind more strongly, or if we change this group, and this one will bind more strongly with protein or something like that. So if we know the structure, then we can get hints. How should we design new drugs? So this kind of simulation, this kind of calculations are very, routinely and widely used in drug companies these days. So let's talk about the goal of protein-ligand docking more specifically. So what is the goal of protein-ligand docking? So the first goal is sampling of conformational space of ligands. So the conformational space means that, so the sampling. So, what is sampling? If you go to a bar, so generally they have a sampler menu, right? So if you order a beer sampler, what do they give you? They give you a whole bunch of beers, spirits in a small amount, right? So the sampling means that you try many possibilities. You try, many possible choices. So in protein-ligand complex, actually, so if you think about, so you know the structure of protein and you know the structure of ligand, but you have to find out how they will bind. But when you bind them together, so actually there are many possibilities, right? There is, it's not just only one possibility. So you can combine it, you can dock it, so in many possible ways. So these are the examples. So these are the docking simulation results. So if you insert a certain ligand, if you attach certain ligand to a protein, so there are many possibilities it can be bound. So the first goal is we want to identify the correct complex structure. And why is it hard? Why is it difficult? So the reason for the difficulty is that, as we all know, so generally chemicals are flexible. Chemicals can rotate, have rotatable bonds. So in English they are called rotatable bonds. So rotatable bonds, it means that bond can rotate. But some bonds are rotatable, some bonds are not rotatable. So as you have already learned in organic chemistry class. So if you have many rotatable bonds, so the ligand can have multiple structures, many different structures. So we have to consider all those possibilities. So that's why the problem gets very complex in general. And also, the proteins are also flexible. Side chains can rotate. Some side chains can rotate. At 300 Kelvin, our body is generally 310 Kelvin, right? So at 310 Kelvin, proteins are dynamic. Proteins are moving, so they are not static. So they are not frozen. So proteins are also flexible, and ligands can also rotate. So that's why, you know, considering many possible structure is hard. And also the second thing is that the scoring of the goal of protein-ligand docking is the scoring of protein-ligand interaction. So the second goal is that to predict how, you know, protein and ligand will bind, how strongly they will bind. So that is in general called, binding affinity. So the binding affinity means that how strongly they will interact. So let's write a very simple, reaction, chemical reaction. So there's a protein and there's a ligand, and we can think about, complex formation reaction. So they two are bound. They are just bound. Then we can think that all the chemical reactions comes with its free energy change, right? And what did you learn from physical chemistry class? So all spontaneous reactions have minus delta G's, right? So if delta G is minus, this one occurs. If delta G is positive, larger than 0, so you need to give some energy to make this occur, right? So if delta G is more negative, it means that protein and ligand bind more strongly. So we want to know, so generally, how strongly two molecules bind. And think about it, and what is the best to become a drug? So a strong binder or a weak binder? Generally strong binders are better, right? So if protein binds with if a drug binds with a protein, weakly, then so in order for a drug to work, so we have to eat it a lot, right? If only 1% of drugs bind with protein, then so we have to, let's say that we have to, take about 10 milligrams. But if some ligand is 10 times stronger than that, so we can only take 1 milligram of pills, right? So we generally want to have small pills, we don't want to eat this kind of big giant pills, right? So generally stronger binders are preferred, are better. So generally people want to predict, so without doing experiment. You can always do experiment, but experiment needs money and time of a grad students, right? So you don't want to do so silly experiments all the time, right? So people want to predict the binding affinity, using computer without doing experiment. So for example, so we have let's say these many of candidates. So these can be drugs, but without doing experiment, so we want to identify, so we want to predict, so which one will bind the most strongly. So then, so we can test it that first, right? Then we can save money and time. So let's look at the one example of protein-ligand docking, and so in the case of HIV protease. So you know what is HIV, right? So HIV is also known as AIDS, the disease, right? So and HIV virus. So you also learned about virus, right? So what is virus? Virus is in between so the life and non-life forms. And virus only consists of DNAs. They only have DNAs. Then how do they replicate? So when virus is, and when a person is infected with HIV, and HIV virus goes into your cell, goes into your body, and it releases its DNA. So this is the virus DNA, and this is your DNA. And this one, so this released DNA goes into your cell. This is the nucleus of your cell, and it is fused with, combined with your own DNA. So it becomes, hybrid DNA. And from this hybrid DNA, I mean, so, but I mean, your cell, your host cell, I mean, doesn't know, I mean, so whether it is combined with HIV virus or not. I mean, it just, I mean, transcripts, I mean, so, as always do. And so when this, I mean, AIDS virus is combined with your DNA, I mean, so everything is just, I mean, transcribed. So your own proteins are generated. At the same time, I mean, you know, AIDS viruses, I mean, proteins from AIDS viruses are generated also. And so these, I mean, red lines means that the peptide synthesized from DNA virus, I mean, the AIDS virus information. And once they are formed, actually, I mean, they should be cut, they should be chopped into several pieces to work as proteins. So actually, so once HIV virus is transcribed, so it forms a very long single chain. And until now, I mean, this is not protein. This is not folded. But once, I mean, they are cut into, I mean, 9 pieces, and those 9 pieces, each piece are folded and work, and they attack your cells. So they should be properly chopped. Chopping means, I mean, so they should be properly cleaved. So the cleaved is a more, you know, intellectual term. But anyway, so that's how AIDS work. And so once, I mean, those proteins are chopped, and they work, and they reproduce their DNA, and they form, I mean, they replicate, I mean, themselves again, and that's how they work. So this long protein chain must be cut, and one of the most important proteins in HIV, in AIDS virus, is called, I mean, HIV protease. So this is the structure of HIV protease. So protease means that in biochemistry, something A's means that it cuts something, and protease means that it cuts protein. So actually there is a hole, right? So there is a tunnel. And through this tunnel, I mean, long protein chain, long peptide chain goes through. And once it goes through, I mean, so and at certain spot, at proper spot, I mean, so it cleaves. It cuts a long protein chain into 9 pieces. So this is the essential enzyme that cuts the long DNA into 9 pieces. So this is one of the most important protein in HIV virus, from HIV virus. So people, I mean, studied, I mean, AIDS virus, and they realized that, oh, I mean, so this one chops, I mean, this one cuts the protein chain. And people thought that, I mean, so, oh, I mean, if we design a drug that blocks this, I mean, so this one, I mean, binds this protein, HIV protease, very strongly, and this one, I mean, blocks the tunnel, right? I mean, so once the drug is bound here, I mean, so it is blocked, right? Tunnel is blocked. So tunnel is blocked, and protein peptide chain cannot go through. So it doesn't go through, I mean, so it is not cut. So it is not cut, then and HIV virus cannot replicate, cannot copy itself. So that's how one of the, I mean, AIDS drugs, I mean, work. So actually, I mean, so this one works quite well, and so these days, I mean, so AIDS is not so lethal, I mean, not so dangerous. So the death rate of, I mean, AIDS patient is almost similar as with a cardiac disease. You know, cardiac disease means heart disease. You know, I mean, so, I mean, people die from heart disease and all of the things. But these days, I mean, so if you take proper medicine, proper drugs, I mean, so you can live, I mean, normal AIDS patients can live up to 70s and 80s. So it's just a manageable disease these days. So anyway, so this is one of the examples. So this is how they work, and generally, you know, the drugs work. So if we know the structure, then we can design, you know, I mean, specific, I mean, the right ligands. So this is the summary slide. And so why is predicting, I mean, protein-ligand docking difficult? So the first is sampling problem. I mean, so among many possibilities, and so we have to find the one right structure. So how will they bind? I mean, so the structure of protein and ligands are generally flexible. I mean, they are rotatable, And also the structure of proteins may change if proteins bind, and also the ligands can have multiple conformations, multiple structures. So there are many possible structures, but we have to find only one right structure among them. And also the second problem is called the scoring problem. So the scoring problem means that so we have to correctly identify which pose is the best and which pose is worse. So it is hard to calculate accurate binding free energy. So and why is it difficult? So the first one is so proteins and ligands generally consist of many atoms. So they are big molecules, right? So they are much bigger than organic molecules. And it is really impossible to run, solving shredding equation for a protein because it is too big. So it is too big with the modern computer. So maybe after 50 or 100 years later, so maybe we can solve quantum chemistry of protein, but it is impossible right now. So and also so the entropy and also in order to calculate free energy, so you have to think that so what is the definition of delta G? So delta G is delta H minus T delta S, and this one is generally energy, energy. And this one is entropy. Entropy is coming from what is the definition of entropy? Definition of entropy is the log of omega. So the omega is like the number of possible states. So the entropy, in order to calculate entropy, we have to know so how many states are possible for a complex. So how many structures are possible. But it is really hard to count all possible structures. So because there are too many possibilities. So the calculating entropy is very hard. So generally energy functions are not accurate enough. So let's look at a little bit more detail of the protein-ligand docking algorithm. So what is the basic assumption? Basic assumption of protein docking. So the basic assumption is that protein ligands will bind to structurally complementary sites. So the complementary means this one. So if you find the word complementary in dictionary, so you'll say this one, but you know that word, right? So the complementary means that so once it completes something by docking. So for example, so when there's a protein looks like this, so we can easily imagine that so it'll like to bind with this kind of shape of ligands, a ligand with this kind of shape, right? So think about it. So when we have a ligand that looks like a star shape or just a rectangular box, then it will not fit in, right? So we generally want to find something that fits well into a protein. So that means structurally complementary. And why is it so? So here, this is the protein surface, and this one fits to its protein surface very tightly, right? Then why is it? So as I explained before, so the generally van der Waals interactions increase as the number of interacting atoms increase. So if more atoms are interacting, if more atoms are close, then van der Waals interactions are generally large. So when you have more contacts, so more so the contact points, so you get more scores. So because so if this is complementary, then so they all these surface, they all have attractive interactions, attractive van der Waals interactions, right? So they generally have stronger van der Waals interactions. Then how do we define? So how to define binding sites and structural complementary. Oh, and also so this kind of site so where a ligand bind is generally called binding sites. So you've seen protein structure during the practice session, right? So if you draw a protein, so it generally looks like this. But I mean, you can also draw a protein surface. I mean, you can think about the protein surface. Actually, I mean, so this one is actually a simplified picture. I mean, so because I mean, so they are all, I mean, all atoms and bonds are shown as just sticks. But if you think about an atom, I mean, if you think about an atom, I mean, so for example, for carbon, I mean, so the electrons are spread, and so the carbon actually, I mean, so you can think, I mean, carbon as a sphere, and you know that, I mean, so then what is the radius? What radius carbon? I mean, so we know that, I mean, so this is the van der Waals radius, and so we learn about the radius of atom, I mean, so during the general chemistry class, right? So because of those radius, because of van der Waals interaction, because of this repulsive term, so I mean, imagine that some atom is approaching to here, then I mean, so because of van der Waals interaction, I mean, so it cannot, you know, it cannot penetrate, I mean, so it cannot go through a protein, I mean, so if they become too close, I mean, so they will, you know, repel each other. So if you think about, if you imagine, I mean, so all atoms are like balls, they're spheres, then you can draw surface like this. So here, I mean, so the surface is shown, and this is somewhat transparent. So if you think about, I mean, so if you look at, I mean, so if imagine that you have a very good, you know, microscope, and if you look at, I mean, protein, then it will look like this kind of dough, right? Like a pizza dough. I mean, so because of surface, I mean, so you cannot, I mean, if you don't have a, you know, X-ray them, then I mean, so it will look like a pizza dough, I mean, because of this surface, because of van der Waals interaction. So from the surface, I mean, so we can find out, I mean, so which one we can imagine, I mean, so we can predict, I mean, so which site a ligand will bind. For example, here, I mean, so where will ligand bind? I mean, so we can easily imagine that, I mean, so, oh, there's a hole, I mean, so the small molecule will fit into that hole, right? I mean, so it's very easy to, you know, imagine. So that's the basic concept. And if you think about other, you know, many examples like this, and so for example, so this is the protein surface, and the ligand is embedded. So ligand is bound with the protein. I mean, as you can see, I mean, so there's a, you know, some kind of pocket, you know. And also, I mean, so this is the interaction between DNA molecule and protein, and for many DNA binding proteins have something like, I mean, this kind of, you know, I mean, so this kind of site, I mean, so this kind of, you know, concave site. So I'll talk about concave in the next slide. So in order to predict, I mean, so where a ligand will bind, and so we have to know, we have to generate, I mean, so we have to generate protein surface, and one of the most famous, I mean, algorithm to generate protein surface is called, I mean, Lee and Richardson surface. So here, I mean, Lee is the doctor, I mean, Prof.Lee, so who worked in NIH. I mean, so now he's over 70, but I mean, so he's one of the most famous Korean scientists in US, and so his paper was, I mean, cited more than, you know, I mean, so several 100,000 times, and so he devised an algorithm to find out the protein surface, and the way he finds out the protein surface is that, I mean, so let's assume that, I mean, these are protein atoms, and you roll a probe, you roll a ball on protein. Then, I mean, so if you follow the center of ball, then, I mean, so you can draw these dotted lines, right? So these dotted lines form a protein surface. So that is also called as accessible surface area. Accessible means that, I mean, so you can approach, I mean, you can touch. So the accessible surface area means that the surface that water molecules can touch. So that's how generally people generate a protein surface. And for ligands, generally, I mean, so bind to pockets. I mean, as I told you, I mean, so generally, I mean, ligands are bound to a concave spots on protein surface. What is the concave? I mean, so you may not be familiar with the word concave. So the concave means this. So generally, ligands bind to a concave spot. Why? I mean, so as I told you before, I mean, so if something is bound in concave, I mean, so it can interact with more atoms of protein, right? So let's assume that so ligand is bound here. So it can only interact with this one. But if ligand is bound here, then it can interact. It is surrounded with this number of atoms, so it has more interactions. So they are more strongly bound. So also, so this is their concave spot, and this is also a concave spot, right? So so what is the opposite of concave? So the opposite of concave is convex. So if something is bound here, then it doesn't have many spots. So only so this spot will interact with the ligand, so it cannot tightly bound. Yeah, you can easily think that once you have a ligand, so you want to surround it to interact with it strong.
저기 좀 질문인데요. 리간드가 콘케이브처럼 생겼으면
근데 리간드는 작으니까.
그렇게 생길 수가 없는 거죠.
근데 이제 뭐 DNA 같은 경우에는 그럴 수 있죠. DNA 같은 경우에는 뭐 그렇게 생길 수가 있는데 그렇다면은 이제 뭐 어쨌든 이제 이렇게 이제 상호적으로 이렇게 들어갈 수는 있겠죠. 근데 보통 여기서 우리가 리간드라고 얘기를 하면 이제 스몰 몰레큘, 오가닉 몰레큘 얘기하니까 오가닉 몰레큘은 프로틴에 비해서 훨씬 작으니까 이제 뭐 예를 들어 단백질이랑 단백질이 붙는다고 하면은 뭐 그런 경우는 생길 수 있는. So let's talk about scoring functions, and so once we have multiple structures, and so we have to score which one is the best and which one is worse. And so to predict binding free energies, so generally so we have to consider these kind of energy interactions. So the first one is electrostatic, so as we talked before, and the second term is van der Waals interaction, and the third one is solvation energy. So the solvation energy means that when you have a certain molecule in gas, so from gas to it is solid to water, there is also a free energy change. Will it like to be dissolved, or will it dislike this? So there is also free energy change. That is solvation energy. So whether it likes to be, dissolved, or whether it likes to interact with protein. And so these three energies, electrostatic, van der Waals, and solvation, are the main, generally, in many cases, the most important energy terms of protein-ligand docking. And also, in general, in biochemistry, in biophysics, so the scoring functions can be classified into two types. So one is empirical functions, and one is called physics-based functions. So the empirical means this, and it is based on experiment. So we fit parameters. And the second type is called based on physics-based, is based on the physical laws, like F equal ma or something like that. And also remember that so every program, there are many protein-ligand docking programs. Some programs are very expensive because they are used in drug industry. So but every program has different scoring functions. So it depends on how you make it. So that's one topic of research. So generally, so the empirical scoring function means that you have experimental data. So you have experimental delta G data, and you fit it. So you first assume your function, scoring function, and you fit parameters to reproduce experimental data. So that is generally called approach called empirical. So the empirical means fitting to experimental data. So this is one example of empirical scoring function. So here, the authors decided that so we're gonna consider only hydrogen bond and ionic interaction and interaction between aromatic groups, and we'll think about hydrophobic interactions or something. We're gonna only think about only these 3, 4, and loss of entropy due to binding. These 5 terms. So the loss of entropy means that so when ligand is solvated in water, so it can freely rotate, right? But once it is bound with a protein, so it cannot rotate freely. So it means that entropy becomes lower, right? So free rotation means high entropy because it can have many possibilities but once it is stuck with one structure, then entropy is low, right? So they decided to consider only these terms, and they fit parameters based on experimental data. But on the other hand, so the physics-based energy function means that energies are based on physical laws. So, for example, so that here, all non-bonded interactions are calculated with this. So here, so this is van der Waals interaction as we learned in our textbook, and this is the Coulomb interaction. Electrostatic interaction we learned from the physics textbook, right? So by using this form, so we can also predict the energies of protein-ligand interaction. So it really depends on so the philosophy of research. So the parameters are obtained from quantum chemical calculations, not from experimental data. So they are hard. So this is an example of how to sample ligand conformation. So this is an example of anchor and growth algorithm. So the anchor means that anchor is a, I should have put some picture here. Anchor means anchor는 닷이에요, 닷. 배에 닷 있잖아요, 닷. Anchor means that so the ligand this is one example. So there are many possible ways, but so for example in anchor and grow algorithm, so we divide this ligand into fragments, into small parts, and we choose the largest part. Oh, here this is the largest, non-separable. This one is rigid, right? This one doesn't rotate. This is a ring. So this is a rigid structure. Okay, I will put this one first. So it can go to here, or it can go to here, and it can go to here. So this is called anchor, the starting point. So anchor and grow means that so you attach so small fragments based on that. Starting from here, so you can attach the rest of the molecule, or you can attach the rest of the molecule, or you can attach the rest of the molecule, or something like that. So this is the one example of how to generate so different structures. So for example, they started from here and they grow the rest of the molecules like this. Or here, they started from here and they grow the rest of the molecules like this. And so there are many ways to generate possible structures, but the key point is that so the ligand can bind to a protein in multiple ways, and among them, so we have to find the best structure. So okay, so that's it. And so as I told you before, 그래서 이제 지난번에 얘기했던 대로 금요일에는 휴강이고요.